So I think we're good whenever you want to start, Matt.
Okay, great. Well, thank you for inviting me to speak in this SL2 group. So, well, I guess I want to explain a few things. So when Jordi invited me to speak, he kind of proposed that I should maybe say what it is that I would like to know about SL2 over finite fields, especially the rep theory and defining characteristic, where I think I was also kind of standing in for maybe some group of number theorists more generally, as some sort of representative member. And so I'd like to do that. So I have to say from the beginning, I don't have a very good sense of what's known. I mean, this kind of conversation, at least between me and Jordi, began with me emailing, asking questions about some things that may or may not be known, but I knew nothing. I mean, and I still kind of know nothing. So, but my kind of experience overall is that some of the questions about rep theory of sort of SL or GL2 of finite fields that number theorists ask are maybe a little bit different to the ones that modular representation theorists are kind of routinely studying. And so I don't know if that's because they're easy, hard, just don't seem relevant from a pure rep theory point of view, or just people haven't got into them yet, or people have got into them, but I just don't know that they've got into them. So I'm hoping that that's one thing that might come out of people's response to what I have to say. But I also want to begin with a little bit of background about kind of where number theorists are coming from. And I could talk about automorphic forms in the Langlands program and so on, but that can take infinitely long. And I'm sure everyone here has sat through various infinitely long versions of such talks already. So I don't want to really do that. I want to talk about a construction that comes out of sort of algebraic number theory in the Langlands program, which is called or Taylor-Wiles patching, or sometimes it's called Kiss-and-Taylor-Wiles patching. And I'm just going to, because there's a question of which proper names you should attach to it, and I don't want to get into that too much, we'll just call it patching. So this patching was kind of a new method that was introduced by Taylor and Wiles to prove modularity of elliptic curves. And it began life as a very strange, weird construction, and it got refined over time. And it's now really understood to be kind of a functor. And what kind of a functor is it? It's a functor which, just for traditional reasons, is called M sub infinity. So I'm going to call it that just because that way, if you look in any paper about this and you see M sub infinity, you'll recognize it as one of these functors. So M sub infinity will be a functor. Well, there's going to be a lot of such functors. They depend on a lot of auxiliary choices, but the domain of this functor is reps of GLN of OK. So what is K? So K is some finite extension of QP. And so OK is the ring of integers, and GLN OK is GLN of OK. So here N is any integer N. And I'll say some things for general N because they're true for general N, and then I'll probably fairly soon specialize to N equals 2, which gets closer to this seminar. And the key thing is these reps, well, they could be in characteristic P, or more generally, they could be in mixed characteristic. So I want to think of them. I could put here ZP. ZP has the advantage that it's ZP, and we all pretty much know what it is. It has a disadvantage that, for example, even in characteristic 0, the irreps of GLN OK, or the irreps of GLN of the finite field, they may not be the absolutely irreducible reps may not be defined over ZP. So normally we would kind of choose some, maybe there's some auxiliary bigger field, that some field E that's a finite extension of QP, and look at the ring of integers inside there and just make it big enough to handle everything that comes our way. Or we could even take it to be like the ring of integers in OCP. So let's go all the way to the completion of the algebraic closure of QP and look at the ring of integers there. And now you've just dealt with all kind of rationality problems. So it doesn't matter too much exactly which of these rings I put. I'm not going to fuss about it, but they're mixed characteristic, and it's going to map to modules over certain complete Noetherian over a certain complete Noetherian local ring. Now this complete, I'm going to try and give an example later. So this complete Noetherian local ring is going to be some pretty specific local ring. So I'm going to get this.
What do you want to think of it?
Say again?
Is there a good letter for it?
We could just call it R. And for those who kind of know something about this story or trying to match it with what they know, this R will be something like, sometimes it would also be called R infinity, and the infinity is sort of matching the other infinity. But the reason for this subscript infinity is a purely like accidental kind of reason that evolved in the subject, and you shouldn't read anything into that notation. And maybe indicates there was a limiting process involved in constructing this functor. And but this R infinity will be some like a power series ring over ZP, or maybe a power series ring over ZP modulo some equations. And I'll give it some more concrete examples later. But it's going to come about, it's going to be a certain Galois deformation ring. But I don't want to sort of talk too much about the number theory that gives rise to it. I want to show the kind of rep theory structures that come out. And the thing about this functor is it's going to be exact and co-continuous. Sorry, I'm not sure what I wrote, but what I meant to write was co-continuous. So it commutes with colimits, which I think is just to say that I probably only have to think about the way it's defined on finitely generated modules. Like if I have a finitely generated module with with an action of this group, and I know what M infinity does, then any module is some kind of direct limit of finitely generated modules. And so so this co-continuity is just saying that I don't have to worry about kind of infinitely generated modules. They don't play any special role. And the exact is kind of the key thing. And it's typically not going to be faithful, except in maybe some very, very special cases, because it's going to factor through a certain quotient of the representation category that depends on the situation. So there are lots of different examples of these functors, but they typically factor through a set quotient category of the representations. So how can we make set quotient categories of the category of representations of GL and OK? Well, the simple objects in that category will be the irreducible representations of GLN of the finite field on over, say, FP bar. So let me just let me maybe be in this case of coefficients, just so that then I have FP bar is the kind of residue field. So there'll be some quotients where we kill off all but a certain specific set of, well, of simple objects. But again, what is a simple object in this category? So because we're looking at modules over OCP, the simple objects will be the representations that are irreps, well, of GL and OK, but in characteristic, but there'll be irreps. I mean, the simple objects will be in characteristic P, and there'll be reps a priori of GLN of OK, but actually, because you're in characteristic P, the pro P subgroup of GL and OK will act trivially, and so they'll factor through GLN of the finite field quotient of OK. So up here, right, this thing has a surjection onto GLN of the residue field. And so by inflation, just thinking of reps of GLNK as reps of GLNOK, reps of GLNK is sitting inside reps of GLNOK. And so a simple object will be an irrep of GLNK over sitting in characteristic P, so with over FP bar. So we could kind of look at the Sayre quotient where, you know, there's a list of these irreps, and maybe in Jordi in his talk last week discussed what they look like for maybe for SL2 of a finite field of, you know, a field of characteristic P. So we're going to choose. I mean, they're going to be certain sort of specific sets that we of simples that we keep, but all the other ones we'll set to 0, and we'll take the quotient. So we'll look at the fixed Sayre subcategory that's kind of generated by all the irreps we want to kill off, and then that will be killed off by this functor. So that's a kind of
I should assess.
Yeah.
This ring R. This is not a Vit vector construction. I shouldn't be thinking of the Vit vectors for R.
You should be thinking of like well, ZP, or maybe my coefficient's now OCP, but that doesn't matter too much. Whatever that coefficient ring was, I chose, but then add some power series variables.
Okay.
And then maybe add some equations. But I'll hopefully in like 5 minutes or so, I'll be able to give some kind of example, and then
cool.
we'll see.
It's commutative.
Thank you.
Yeah, it's a commutative. Yeah, it's a commutative.
Sorry, can I ask again? Which ones do you kill and which ones do you keep?
So it depends on which patch. Ultimately, the way you build this is you would choose a Galois representation of the absolute Galois group of K, a rep of that Galois group into FP bar, yes. And depending on which an n-dimensional one, and depending which one you chose, you'll get a list of irreps that you keep and all the other ones you would kill. And again, maybe I'll give you an example in a little bit, but it is which for a given Galois representation, which ones you keep and which ones you kill, that's related to what's called Sayre's conjecture. Although it's called the weight part of Sayre's conjecture. So number theorists have this name where these simple objects, we call them Sayre weights. Mm-hmm. And for each residual Galois representation, for each representation of GK into GLNFP bar, we have a list of Sayre weights for that representation, at least conjecturally. Maybe it's not proved completely in general what the list is, or that the list is well defined, but there's supposed to be a certain list of these irreps attached to that, and those ones you want to keep, and the other ones you're going to kill. But
can you characterize them categorically inside the big category? No.
Not so. I mean, in a way, I'll try to give you an example, and you'll see sort of how they categorize a little bit for GL2, and then again, I think that the way we think about them, we being number theorists think about them and characterize them, is going to be super different, I would guess, to structures that would occur naturally if you're just doing the rep theory. And that's part of what I want to maybe just give a sense of in the talk, is just that these objects exist. And there's some population of mathematicians who are kind of thinking about this topic in probably quite a different way.
Good question for you to rule out off the bat. Is this functor M monoidal at all?
No.
Okay.
Definitely not. So the kind of thing that here's like so one thing I could say about this functor, although I probably won't come up too much in the rest of what I say, is that it's actually defined on a category which contains reps of GLN and K, but has more morphisms. So as well as just the obvious morphisms in that representation category, they are heck operators. In other words, you can take reps of GLN OK and you can induce them up to reps of GLN of K. And induction is a functor, but if you have 2 reps of GLN OK, they can be maps between the inductions that don't come from maps between the representations that you induced. Those extra maps are normally what number theorists or automorphic form people call heck operators. And this thing is functorial for heck operators too. So it has, which just means that there's kind of, there are even more morphisms in the category, and it's respecting those as well. So it doesn't, nothing that I've written is false. I just haven't written everything that's true. So so for example, the so here's a model for what this functor would be. Suppose I had a group gamma. In fact, probably later on, just to save notation, I'll call GLNK gamma. So let me just say I have a group gamma, and suppose I had a classifying space for gamma, and I could make local systems out of reps of gamma, and that would be an exact functor, passing from reps of gamma to local systems on the classifying space. But then I could take cohomology. Well, that wouldn't be an exact functor, but if I took it in a particular degree, I could take maybe cohomology of these local systems in some derived sense to get some kind of triangulated exact functor or something. But in any case, that will be a functor that's still exact, maybe to Z modules or ZP modules, but it would not be monoidal anymore. But imagine now that this space had extra symmetries. Imagine that I was in some situation with extra symmetries because I was doing automorphic forms. So automorphic forms gives you lots of classifying spaces for lots of different kinds of discrete groups floating around, and lots of local systems with lots of Hecker symmetries and other things. So then you could imagine that what I just described would produce not just Z modules or ZP modules, but modules with extra Hecker, some extra symmetries. And that's kind of where this functor M infinity is going to come from. But the kind of model you can imagine is some sort of like, you know, taking cohomology, basically so that's purely group theoretically, taking total cohomology of gamma representations, which will be a triangulated exact functor, but not a monoidal functor. And that's kind of what we're getting at. But the kind of thing that, like one of the basic questions number theorists would like to prove is that this M infinity is actually uniquely determined by some maybe small amount of input data. And like what kind of input data might one have? Well, one might know what the ring R is, and I know I haven't said anything about it, but again, I'll do a big reveal in a little bit as to some examples. But you might also know what this functor does on the simple objects that it's not killing, and then anything else is built up out of extensions of the simple objects. And so if you understood extensions in the category of representations very well, you might start to be able to predict what your functor does, like, because since it's exact, an extension on the rep theory side will be taken to this functor to some extension on the module side. And I don't want to get into exactly how you would handle the extension theory on the module side. That will be its own story. But at least to begin the process I've described, you'd want to understand extensions very well on the rep theory side. And so what this means is that number theorists have a big focus on thinking about extensions of the reps of these group, well, GL and OK, but in particular GLNK. I mean, GLNK is kind of just restricting this functor to GLNK representations is already kind of interesting and worthwhile. So, but somehow that's so this is why this is sort of, well, I said the question I asked Jordi that prompted this whole discussion between him and me, and then me talking here, was about extensions of GO2 FQ representations. And it's studying these patching functors is kind of the motivation for why number theorists want to understand the extensions. So, so I want to give some sort of say something more precise about this functor, some more specific examples, so you can see something about what I'm talking about. And so for that, I want to focus on GLNK, but even I want to just focus on the case n equals 2. And again, I'll focus on representations that are actually reps of gamma of GO2 of the finite field. Rather, and as I said already, when I just look at this functor restricted to reps of GL2K, even if I don't throw in the whole picture of the rep theory of GL2 of the ring of integers, even if I just look at the GL2K case, it's still an interesting functor that number theorists would like to understand better. And so, so the situation that number theorists find themselves in is they build this functor very much the way I described the toy model, out of cohomology of local systems, but they connect it also to automorphic forms. And automorphic forms are related to cohomology via basically Hodge theory, which means that you have to start with characteristic zero representation theory to connect to automorphic forms. And so the sort of starting point for number theorists would not be the simple objects over FP bar, but instead the E-reps over E, or over CP, the E-reps over the coefficient field. So the E-reps of gamma over, say, CP, or any algebraically closed field of characteristic zero, as you know, fall into various kinds. So one thing I should say is I know this, as an aside, is this seminar is like about SL2. And maybe from a rep theory point of view, SL2 is slightly better than GL2 just because it's semi-simple. But from a number theorist point of view, GL2 is better than SL2. We would never do SL2 until we'd already done GL2. But often, I don't think it makes so much difference for a lot of the questions. But in any case, everything I'm saying is for GL2. And hopefully that's kind of okay. But the E-reps will be kind of, they could be one-dimensional, just, a character composed with a determinant, or they could be Q-dimensional, which is like a character composed with determinant tensored with a Steinberg. And these cases are going to be regarded as somewhat exceptional for the stuff I'm talking about. Often we would say they were not generic. And then the next cases we would talk about degrees of genericity, but these guys will be the maximally non-generic ones, and then the kind of more generic guys will be Q plus one dimensional, which is the principal series, the irreducible principal series, or Q minus one dimensional, which are the cuspidals. And again, if you're ever in a conversation with number theorists about these things, these are often by number theorists called tame types. So tame here is more or less referring to the fact that they're reps of GL2 of the ring of integers that are factoring through GL2 of the finite field. And types are the number theorist word for certain representations of GL2 of the ring of integers that play a particular role in the representation theory of GL2 of the p-adic field. So when you study infinite dimensional representations of GL2 of the p-adic field, the GL2 of the ring of integers inside GL2 of the p-adic field is a maximal compact. So when you restrict this infinite dimensional representation for GL2 of the p-adic field to GL2 of the ring of integers, it breaks up into finite dimensional reps of that maximal compact. Infinitely many finite dimensional reps of that maximal compact. And some of those are kind of more important than others. the ones that are kind of the sort of the most important are called types, and so they play a special role in the Hecker theory and in the classification theory and in the theory of the Bernstein center. And but in the tame case, when you're looking at representations of GL2 with a finite field, everything is a type. So so we call these tame types. And so one thing about these tame types is that, of course, when you're doing rep theory of this, of GL2 of this finite field in characteristic 0, when you think about building these, you can think about building them out of, as a special case of Deligne-Lustig theory. And I guess there's kind of a point of view where maybe like the principal series look much easier maybe than the cuspidals, like they may be easier to construct. And in like Deligne-Lustig theory, the principal series would just come from some kind of function supported on a finite set of points, on the FQ points of the flag variety. Whereas the cuspidals, you would have to take some complement of the FQ points in the flag variety, and then take some cover, and then take a sheaf, and then take homology, and the cuspidals would look much fancier, harder to build, and harder to classify, and just whatever. But from our point of view, so what is our point of view? That we're looking at really representations over ZP bar or OCP. We're looking at representations of mixed characteristic. The cuspidal and principal series don't look that different. They don't look more or less complicated than each other. And there's a precise sense I want to give to that I'll try to explain right now, which is that when we look at these tame types, the kind of things we're going to want to compute our functor on is not so much these types themselves, because that will kind of, on these types themselves, you've inverted P, which means you're working over a p-adic field and you're in characteristic 0. And we're number theorists. We want to have integers, not rational numbers. So we don't want to invert P. So we want to work with lattices in these tame types. So there are lots and lots of lattices. Let me kind of just exclude these guys and look at the other, because these guys, I mean, of course, a one-dimensional vector space up to scaling has only one lattice inside it. And because the Steinberg is irreducible even in characteristic P, these twists of Steinberg also only have one gamma invariant lattice inside them up to scaling. But these bottom guys have typically lots of lattices, and the reason is that these guys are not irreducible when you reduce the mod P. So that's the special role. Well, even if we were in characteristic, even if we were kind of doing L-adic representations of gamma, and then we reduce mod L, some statement like that could be true on the margins. Like there can be some principal series types for very particular characters whose reduction mod L will become reducible, but it's only kind of, but in non-defining characteristic, the difference between reducibility in characteristic 0 and reducibility in characteristic L is a fairly marginal difference. But in defining characteristic, it's a huge difference. And so, so let me just kind of remind you of some examples. I'm going to just do GL2FP and then GL2FP squared. So in GL2FP, there's a principal series. If we took a principal series we make by inducing a character from the Borel to GL2. And that description of the principal series makes sense with integer coefficients. Because the character you're inducing, what is it a character of? You're inducing a character of the torus in GL2FP, which is FP star cross FP star. And this character will take root of unity values, and roots of unity are integers. So the character you induce to describe the principal series representation will be an integral valued character. So just the formula for the induction as functions on GL2QP that transform under the Borel by this character makes perfect sense with integer coefficients. And so then you can reduce it mod, it makes perfect sense with FP bar coefficients. So you can kind of reduce it mod P and you get a description of the principal series with FP bar coefficients. And so if you look at if you look at a simple representation who has the highest weight of the character we described, this principal series will map to that highest weight representation. So maybe it's some arithmetic power of FP bar squared. And there could be a determinant twist, and I'm not going to put down the determinant twists because they're annoying to keep track of and they're not important to think about what's happening. So so this is a typical irrep of GO2FP and characteristic P. But the principal series has dimension P plus 1, and this has dimension R plus 1. So this is not that entire principal series. So in other words, if you just write down in characteristic P what it means to have a highest weight of kind of highest weight like R, the principal series is sort of the tautological representation of GO2FP that has this highest weight. And this representation built out of a rep of the algebraic group, this kind of vial module, is an actual irreducible representation of that highest weight. But it's smaller dimensional than the principal series. The principal series subjects onto this thing. So I'll write principal series overline because I've reduced it into characteristic P. And there's a sub, which will be up to determinant twist, which again, I'm not going to keep track of, will be sim P minus 1 minus R, which has dimension P minus R. And if you add those up, you get P plus 1. So this is, I mean, this is terrible notation, but I'm just going to write principal series brackets R, just to kind of remind you that that's the, that R is kind of standing for the highest weight that I built this principal series out. But I want to remind you of two things. First of all, principal series R is isomorphic to principal series, well, again, up to some twist, P minus 1 minus R. Like there's an intertwiner between, if I choose two characters on the torus for GO2FP and I induce them in characteristic 0 and I get a principal series, and I flip those two characters, I get, the induction is the same. There's intertwiners between principal series. So principal series, which in my notation will be like principal series P minus 1 minus R, is the same representation. But if I write down principles, but if I reduce that mod P, I get a different picture. The role of R and P minus 1 minus R is swapped. Why is that? So one thing I should say is that in this picture, and so similarly in this picture, the extension is non-split. So these are definitely not the same representation. So how could that be? Well, the intertwiner has denominators in its definition. You have to divide by P to write down the intertwiner. So it doesn't work integrally. So integrally, the integral principal series I get depends on whether I chose the highest weight R or the flipped highest weight, sort of that I'm P minus 1 minus R. So those two integral principal series are two different lattices in the same QP vector space, or the same characteristic 0 vector space. In that same p-adic vector space of dimension P plus 1, I have these two different invariant lattices. So their reductions can be different, and in fact they are. So just another thing is, suppose you took, suppose we just had this thing. Could we have guessed about this thing? Well, the answer is yes, because if I have a lattice, the integral principal series, and I reduce it mod P and I get this thing, I could take the pre-image of that part. I could just take the pre-image of the socle in this mod P reduction. And that will be some new lattice, some sublattice of my original lattice, which had a surjection onto this sim P minus 1 minus R. It would exactly be this lattice. So you can kind of see that if I have a lattice that whose reduction has reducibility, I can use the very reducibility of the reduction to kind of create other lattices by pullback, which have different cosoccles and different soccles. And in fact, on the other hand, we at least see that the constituents of PS bar and the constituents of PS bar P minus 1 minus R are the same Jordan-Holder factors, even if they're kind of extended in a different order. And so we kind of remind ourselves that that if you have kind of a characteristic zero rep, and you choose tau circ an integral lattice, and then you reduce this tau circ mod P, the tau circ certainly need to be unique, and so the tau circ even up to scaling, and so the tau circ reduced mod P need to be it's not well defined. It doesn't depend only on tau. It depends on the lattice typically. But the Jordan-Holder factors, which are a multiset, depend only on tau. So that's a kind of easy like Jordan-Holder composition series type theorem. So we could call them just Jordan-Holders of tau bar. So tau bar is not really well defined. To reduce this characteristic zero thing mod P, you have to choose a lattice. So tau bar doesn't really make sense, but its Jordan-Holder factors make sense as a multiset. And if, for example, there was a single Jordan-Holder factor, if tau bar was irreducible, that will be what's happening in the cases I crossed out. Then, in fact, the lattice is unique. Then tau circ, any gamma invariant lattice, is unique up to scaling. But if tau circ is not, if there's more than one Jordan-Holder factor, I've just shown you how to build sort of more than one lattice. I've shown you how to build lattices that aren't equal to scalars of each other. So, you can see another thing that happens with these lattices is these lattices exhibit certain extensions. Like this lattice exhibited this extension of sim R by sim P minus 1 minus R. And this lattice exhibited extension the other way. So if I did a cuspidal type instead, just what I would have gotten will be, it's less obvious how to choose a lattice in a cuspidal type. It's just a sort of abstract. Since gamma is a finite group, we can choose lattices, but you can't make them in quite the same representation theoretic way because the cuspidal type is already hard to make as an explicit construction. But if in the cuspidal type, the extension you get will be, you would see a sim, if you saw a sim R in the socle, or sorry, in the cosocle, you would sim P minus T minus R in the socle. Up to, again, you should put in some twist to make the central characters match, but I'm not going to put in the twist. And of course, you could find a different lattice that had them flipped. And in fact, those are the X1s in the category of GL2FQ representations. If you have sim R and you ask what other simple does it extend by, it extends exactly by this P minus 1 minus R guy and this P minus T minus R guy. And the relation of having a non-trivial X1 is a symmetric relation. And these lattices are kind of producing these extensions and revealing the symmetry. So this is sort of, in some sense, this is connected to how these number theorists get into the question of extensions, because we have these lattices and then we're reducing the mod P and we're finding extensions. And we kind of wonder, like, are those extensions unique? How, could we have predicted them a priori? Questions like this. So I want to remind you now of the GL2FP squared picture, because it's sort of more interesting. Because in this example, the cuspidal case, well, I don't know if you could have guessed how it was going to go, but cuspidals are mysterious anyway. But the principal series case is not so mysterious. The principal series is like some kind of universal tautological highest weight representation. I think of it as like a GL2FP version of a Verma module or something like that. You just impose that there's a GL2FP action, there's a highest weight vector, and you impose no other relation, and you get this principal series. And so then it naturally has a map to the irreducible. And then there's kind of a kernel, and maybe a priori that kernel is mysterious. But when you think about the intertwiner, you kind of discover a flipped picture and you discover what the kernel is. And the dimensions add up to P plus 1. So you know that there were no other Jordan-Holder factors. So you just use the highest weight description of the principal series and the intertwiner to discover two constituents in the Jordan-Holder factors of tau bar. Their dimensions add up to p+1. So you've discovered all the constituents. But something marvelous happens for GO2fp squared, because a typical highest weight representation will be maybe, you might have sim r. So I'll just write sim, since I'm doing fp squared, sorry, I don't know why I wrote fp, I don't know why I wrote the square up there. Hope that wasn't too confusing, because I certainly meant to write the square here. I'm doing a finite field of order p squared. And so I'll write bar for the Frobenius conjugation, just to make it a simple notation. So I have I'm sorry, my bars are all over the place for the meaning. QP, like I had like a bar for algebraic closure on FP bar, and now I had a bar for reduction mod P, and now I have a bar for the conjugation action. But hopefully it's okay. So I have sim R tensor the Frobenius twist of sim S. That's a typical kind of highest rate representation. And then the complement, so that might be, that will be kind of a constituent of a principal series. It would appear maybe as a socle or a co-socle of some lattice. And then correspondingly, if that was the kind of socle, then the co-socle would come from the flipped, the intertwiner would tell us that we will have a kind of flipped picture, which would be P minus 1 minus R, and so P minus 1 minus S. But if you add up those dimensions, they don't add up to P squared plus 1. They fall quite short of it. And also, these two representations do not emit an extension between them in the category of GO2fp squared representations. They're actually 4 constituents typically. So here you get sim P minus 2 minus R tensor sim S minus 1. And here you get sim R minus 1 tensor sim P minus 2 minus S. And these guys, you guys would have been in some sense a bit hard to guess them just a priori. They're not related to either. The principal series can be described as a principal series of one weight that has to do with R and S, or with some kind of Weyl group flipped weight that has to do with P minus 1 minus R and P minus 1 minus S. But doesn't, the characteristic zero principal series doesn't have any obvious connection to those middle weights, but they're what appear in the reduction of a principal series lattice.
Matt, are there bars missing?
Yes, they are. Thank you. Great. I just want to, again, probably lots of people here know the story of X1s, but let me just remind you how it goes. So here there is all the bars. So what I've written is kind of the socle filtration. I've written the bottom, I've written the socle, I've written the next 2 simple pieces of the socle filtration, and I've written the co-socle at the top. On these reductions, the socle and co-socle filtration will coincide. And so those diagonal lines are kind of indicating an extension, and all the diagonal lines are non-split extensions. And that's how non-split extensions go for GO2 of FP squared, or in general for GO2 of FQ. To get a non-split extension, what you have to do here is you have to send either R or S to P minus 2 minus R or P minus 2 minus S. So I'll just call that flipping. You flip one of them, and the other one you modify by either plus or minus 1. For example, if you look at this one, S got modified by minus 1. But if you look at this one, the R entry got modified by plus 1. We went from P minus 2 minus R to P minus 2 plus 1 minus R. So both flavors of extensions are appearing here. A flip and a minus 1 and a flip and a plus 1. Here there was a flip and a minus 1. Here there was a flip and a plus 1. Here you went kind of minus plus. You went minus plus. If you started here, so there'll be a lattice that has this thing as the co-socle, and there you will go kind of plus this way, and minus this way, and then, minus this way, and minus this. I think plus and plus, and minus and minus. So you can sort of, depending on which lattice you choose, you could, for example, have multiple elements in the socle, but certainly you can choose a lattice that has any one of these weights in the socle, and has any one of these simples as its socle, and then that lattice will produce a picture in its socle filtration that looks like this square, but possibly rotated so that the vertex you chose was to the bottom of the square. And you can kind of get various arrangements of these plus minus extensions. And you'll see that you kind of get every arrangement that's compatible with the, because if I kind of start at some socle and then I do a plus minus to get an extension, a plus minus and a flip to get an extension, and a plus minus and a flip to get an extension, and then I do some plus minus and flip to get an extension, and some plus minus and flip to get an extension, I may not end up at the same thing at the top. Whereas here, like when I go around the two sides of the square, I end up at the same co-socle. So you'll see that if you think about all the possible flips and extensions you could build with the pluses and minuses, that would lead you to the same thing when you go around each side of the square, a bunch of the possibilities are achieved in this diagram, but not every possibility. There's another possibility where you could have sim r tends to sim bar s, and I'm just going to systematically do minus ones. So I'm going to go to sim p minus 2 minus r tends to sim bar s minus 1. And then I'm going to do sim p minus 3 minus r, and I'm going to flip, so I'll get sim p minus 1 minus s. Then I'm going to come down here, and I'm going to subtract. So this way I should flip s, so I should have sim r plus 1 tends to sim bar p minus 2 minus s. So if I start here and I work my way around the square, here I did a flip in r and a minus 1 in s. Here I did a minus 1 in r and a flip in s. When I go down this way, I did a flip in r and a minus 1 in s. And when I go this way, I did a flip in s and a minus 1 in r. So if I kind of go around the loop, everything was all the extensions of a minus 1 species. And if I went the other way, all the extensions are kind of a plus 1 species. So if you basically look at these two diagrams, you'll sort of, and you imagine starting at any vertex, you'll see that you can basically kind of made all possible arrangements of extensions in a square that start and end at the same representation. And if you add up the dimensions, of course, this one will have dimension p squared plus 1, total dimension. If you add up this dimensions, this will have dimension p squared minus 1. That second thing is reduction of a cuspidal. But you can see what I mean, that cuspidals in principal series mod p don't look so different. Maybe the difference with the principal series is you can predict some of the irreps that appear, some of the constituents in the Jordan-Holder factors, but only two of the constituents. The one that comes from the highest weight of the principal series and the one that comes from its other highest weight when you apply the intertwiner. But we have 4 constituents altogether. And in the cuspidal, I also get 4 constituents. And if I did, if I was doing q equals 2 to the f, I would have typically 2 to the f constituents in these reductions, arranged in a hypercube in the socle, in the co-socle or socle filtration, with all kinds of extensions. So this is, so I say this is a typical behavior because occasionally, if you look in this formula, sometimes you will get some expressions that were minus 1. Like if r was 0, if this r were equal to 0, then this r minus 1 will be minus 1. So when you see a sim minus 1, you interpret it to mean the 0 representation. And in that case, there are only 3 constituents. Those are some kind of limiting cases, but they're unusual. So sometimes when we talk about, if you hear a number theorist doing this theory, talks about generic types, they will sometimes rule out those edge cases where you get some kind of sim minus 1s in these formulas, depending on what exactly they're going to do. I just wanted to point out for people who like numerology that this r goes to p minus 2 minus r and then flip something else by plus minus 1 even makes sense for fp. It's just that in fp there's only one slot. So you're kind of, so you can think that p minus 1 minus r is p minus 2 minus r, but then you added a 1. And the p minus 3 minus r that I had is p minus 1 minus r, but then you, p minus 2 minus r, but then you subtracted a 1. So in the GO2FP case, the flip and the subtraction are happening on the same slot, whereas for GO2FQ, you flip in one slot and you do a plus minus 1 in a different slot. So, so these are the kind of structures that number theorists will study. And the first thing you might do is you might restrict your representation. You might restrict this patching func to m infinity just to the category generated by lattices in a given type. That could already be interesting, because of what I've seen, they're like, there's a bunch of lattices in this type, and these lattices have lots of simples in their reduction, like maybe 4 at least, which is a lot in this game. And so so this functor could be interesting. And so let me even think about GO2FP, where there's only, and fix a type. Fix this principal series or customary type. And then if I think about lattices, we could look at the kind of what I would call the category, just to kind of abuse terminology, I'll call it the category of lattices in tau. I really mean the subcategory of all reps generated by the lattices in tau. So let's look at let's look at lattices in tau, direct sums of those things, and then subquotients of those direct sums. So more or less things you can get by taking direct sort of sums of lattices and then subobjects, and then some other direct sum of some other subobject or some other direct sum of lattices, and then a map between them, and then a co-kernel of that map. These kind of things. So that has projective objects. We know what before I say what the projective objects are, I should say what the simples are. The simples will just be the simple reps that appear as subquotients of this particular type. So that will be, in the principal series case, it will be these two simples. And in the customary case, it will be these two simples. So there'll be two simple objects in this category of lattices. And so each of those will have a projective cover. And what will that projective cover be? So let me, rather than just say projective object, let me say so I'll write sigma for a simple. That's a sort of a standard notation among number theorists. So the projective cover of sigma is a lattice with co-suckle sigma. So in the principal series case, those two lattices I wrote down were two projective objects in this category of lattices. That's fairly easy to check. And so a projective generator equals, check some of these two lattices. So maybe like L sigma 0 plus L sigma 1. Like there were two of these weights, there were two of these simples. So there are these two lattices, and I could take their direct sum. And the endomorphisms of this projective generator will be, well, you have to think about the endomorphisms of this guy. So you have maps from this lattice to itself. Well, a map from the lattice to itself is just going to be, it's going to induce an endomorphism of the, when you invert P, it will induce an endomorphism of that principal series irrep. So by Schur's lemma, it will be a scalar. But it has to be a scalar that preserves this lattice. So it will just be an integer. So, well, I can write OCP, but here I could define these things even over the p-adic numbers. So let me make it a bit smaller and just work over the p-adic numbers and say that it's ZP. That will be what you will get, kind of the diagonal entries. But also, of course, these lattices are in the same type. So you can certainly find maps between these lattices, because if I have any two lattices in this type, I can scale one to be inside the other. And there's some sort of minimal amount that I could scale L, like L sigma. If I fix L sigma 0, and then I think about scaling L sigma 1, there's some kind of minimal power of P I need to multiply it by so that it's inside L sigma 0. So that L sigma 1 is inside L sigma 0. And once I've done that, there's some minimal power of P I need to multiply L sigma 0 by, so it's now inside L sigma 1. And it turns out that, well, the first minimum power of P is not really anything invariant, because that was just a way to normalize the choice of L sigma naught and L sigma 1. So I can kind of normalize them. So L sigma naught is that some choice I made, and L sigma 1 I choose to be scaled, so it's fitting as tightly inside L sigma 0 as possible. And then there's a question of, now what do I need to multiply L sigma 0 by so it lands inside L sigma 1? And that number is P. So that means I could kind of write this thing as this order in a matrix string. So again, if I inverted P, this will just be tau direct sum tau. And so the endomorphisms, since it's a direct sum of an irrep with itself, the endomorphisms will be a 2x2 matrix string. And when I look at this projective generator in this category of lattices, I get a certain order in that matrix string. So I'm going to write this a slightly different way, which will seem weird for a moment, but then will seem, I think, less weird once I explain why I've done it, which is I'm going to write this as ZP, and then I'm going to write X times ZP and Y times ZP and ZP. So X and Y here are just variables, they're symbols, but they satisfy the relation X, Y equals P. So it's just another way to write the same order, except I've kind of, instead of having X equals P, sorry, instead of having X equals 1 and Y equals P, I've let X just be the symbol X and Y be the symbol Y, but their product is equal to P, which amounts to the same ring. But the point is that the functor M infinity restricted to the category of lattices, at least in certain examples, will be, well, I'm not going to describe it directly on reps, I'm going to describe it Morita theoretically. So by Morita theory, I know that an object in this category of lattices is the same as a module over this endomorphism ring, which I'll call E for endomorphisms. And I'm going to tell you where I send an E module. So I embed the ring R will be, in this case, this ring, ZP adjoining two variables X and Y with relation X, Y equals P. And the M infinity of some E module, maybe N, will be N tensored with E on R plus R, because this E, the way I've written it with these X and Y, is it's sitting inside 2x2 matrices on the ring R. I think of the X and Y now as being elements of R. So it's sitting inside the ring of 2x2 matrices in R. And so this is a functor. And that will be,
when you try to unravel the Morita equivalence here, R plus R corresponds to.
So each R will correspond to, like, I mean, if I put E tensor E, so R plus R will be corresponding to the projective generator itself. And each of the copies of R will be corresponding to each of these lattices. So this guy will give you one copy of R. This guy will give you another copy of R. The direct sum, which is the projective generator, gives you, sorry, there we go. You know, like to see where, E itself, we yeah, hopefully I'm not getting myself all muddled. I think I'm just staying in the universe of sanity. I think I'm just staying in the universe of sanity.
Shouldn't the projective generator, like, because normally Morita is hom from projective generator dash.
Yes. So the projective generator will map to E, and then E will go to R plus R. So I'm good. I think everything I said is correct. So the projective generator converts to E, and then E tensor with E is, cancelled out. I just get R plus R. So E, so the projective generator goes to R plus R. Right. Hom from projective generator to projective generator is what E is.
Mm-hmm.
So projective generator as an E module, it's just E itself. And under this functor, E itself is E tensor with E.
Oh, okay. Sorry. I was asking under Morita equivalence, not under M infinity.
Yeah.
What happens?
Yeah. So under Morita equivalence,
some of the simples, or
no. So R plus no. So again, like R plus R plus R is where under this whole functor M infinity, that's where the projective generator will go. The projective generator is a sum of two pieces.
I agree.
Each piece goes to one copy of R.
Agreed.
The simples will go to mod P reduction. So if you reduce this ring mod P, it becomes reducible. R mod PR is FP adjoin XY with XY equals 0. So it has two irreducible components, and the two simples go to the structure sheaves of those two irreducible components. This X is sort of standing for the map from one of the projective lattices, one of the lattices to the other. And so the co-kernel, as I said, like the lattice for sigma 1 can be put into the lattice for sigma 0, and the quotient will exactly be the simple. And so this X is, so somehow when you figure out what's going on, you'll see that the inclusion of one lattice into the other, with the simple being the co-kernel, will convert into multiplication by X from this copy of R to this copy of R. And when you quotient out by multiplication by X, you get one of the irreducible components of the mod P reduction.
Can I ask you? I mean, R plus R. You don't mean a progenerator for E, because E is a progenerator for E, and if you did
R plus R is this ring. What I'm describing a functor from E modules to R modules. So for that, I need a bimodule. So R plus R has an obvious R structure, but it has an E structure as well. Because as I said, I can embed E. I can think of the matrices in E as being matrices in R. So R plus R is an R is an RE bimodule. So R plus R is kind of the bimodule that's achieving.
So it's really the action on vectors.
Yes.
Okay. Thanks. So
yeah,
it's not a projective module. It's not projective for R.
No. But one thing that's already like slightly unclear here to me directly is that this module R plus R is flat over E, as it has to be, because I'm claiming this is an exact functor. But checking that flatness is a little bit, like, I find it slightly non-trivial to check the flatness. I mean, I know it's true because this description is the end of a lot of computations in number theory, and the exactness is like the first input in the series of computations. But to see the exactness by hand here, I find slightly tricky. And if you go to the FP2 squared version, it seems even harder. And I think it's but one thing that happens is that if you put in torsion-free modules N, you'll always get Cohen-Macaulay modules over R. And I think and if you think about what various sort of projective resolutions on the rep theory side, how they get converted into resolutions on the R side, you see stuff that looks a bit like matrix factorizations. So this XY equals P relation to me looks a little bit like some kind of, in the theory of Cohen-Macaulay modules over complete local rings, there's this idea of matrix factorizations, and I feel like I see signs of that here, although I don't know an actual, I'm just like pattern matching. I'm doing mathematical pattern matching when I say that, but that's sort of an example of one of these functors finally, and so the kind of rings, and what one of these functors could look like, and the kind of sets of weight. So just to answer Kaluna's question from the beginning, like the kind here, the weights we're killing off are all the weights that are not the two sigmas that appeared in the reduction of this type. So those are the kind of things we're looking at. But I think I'm kind of out of time, and I haven't got into the questions I want answered. So I just want to, so what I wanted to, I don't know if I achieved any goals. I mean, probably sowing confusion was certainly achieved, but I don't know if anything else was achieved. But what I wanted to do was say that there's this functor with these properties that's sort of interesting, and that there's some interesting synergy where this computation is a Galois theoretic computation. It's a Galois deformation ring. But this relation xy equals p appears also in the rep theory when you describe it by Morita theory. And we don't really know why that happens. Like that's some kind of pretty big surprise. I don't know. It's some like, looks like some miracle. And it suggests that there's this yes.
I don't want to rush you. So does it make sense to have a short break and then you can continue for a little bit and then we can discuss? So the talk can go into the discussion session a little?
Yeah.
So, did you understand what this lattice category was? So the objects are not only lattices, right? Because there was the simples too.
I think it's everything that's generated by the lattices under direct sum and subquotients.
Okay.
But like presumably from the number theory perspective, you're not going to be interested in all lattices, right? I mean, are you really interested in all the lattices? That just seems kind of too difficult. I mean, in general, it's incredibly hard to understand all these lattices.
You usually restrict to the case where the residual representation has multiplicity 1, and so you can actually classify all the lattices.
But also, as soon as you have one lattice, and if you were closed under subquotients, you're going to get all the other lattices.
It's isomorphism classes of lattices. I mean, they're not embedded. You don't think of them as embedded in one.
Hello to everybody I know, by the way. Zoom has this weird thing where I'm looking right at you, but of course you have no idea because you don't know that I'm looking at your photo or your image. But yeah, some people here, I guess I know, but a bunch of people I don't.
So can I ask another basic question?
Of course.
So when you talk about these extensions, how do you compute them in practice? Do you really use that you are in GL2 and then compute explicitly, or do you have some sort of
they are so I guess there's work on in the case say of GL2 or SL2, there are some old papers. Andrea may actually know the references better than me, but for people who work in this stuff, like me and my immediate co-authors, the basic reference we use is a paper of Breuer and Paskunis, which gathered all the information from older references and extended it. And roughly, people compute sort of it's similar to computing the simples. You go from the algebraic group to the FQ group. Mm-hmm. So in the sort of studying you look at certain injective envelopes and you make them fairly explicitly, and then you study the Sokal filtration on these injective envelopes. So things are known for GL2 and maybe for GL3 as well. I don't know what the state is for GLN.
So the ones that are known usually are used for Frobenius kernels, and they compare the injective envelopes in those two categories. And that's where the genericity assumption come in. So I'm not sure what happens in high rank, but the small rank ones that's how it works. And also those papers that Matt was talking about, that's how they compute. They just work with the finite group, but they end up using those kind of results.
For SL2, then And only X were computed by Anderson, Jorgensen, and Landrock, and also by Carson, right?
Yeah, exactly.
But
yeah.
And what is the reason for you to work with GLN?
Because,
I would take it if I do combinatorics, but
no, because like already, if you look at the rep of this finite group, if you look at a principal series representation for SLN, right, there's a special case of a quadratic character where the principal series breaks up into two pieces.
Okay. Mm-hmm.
So in number theory, that phenomena occurs also like for SL2QP and other things as part of what's called endoscopy.
Yes.
So endoscopy is a massive complication in doing automorphic forms.
Okay.
So for GLN, there's no endoscopy. So that's basically the reason.
Okay. Yeah, that makes sense.
Are you familiar with the work from the 90s of Rogenkamp on lattices and things like that?
No.
Klaus Rogenkamp. So this description of if you take the group algebra of a group like a GL2FP, so cyclic pseudo subgroups, you can describe it as a subalgebra of a product of matrix algebra. If you take the group algebra over E over ZP, okay?
Sure.
And so you would want to say that this is given by matrices satisfying certain kind of, I don't know, like congruences or divisibility or things like that, okay?
Yeah.
So that's what he did in the 90s.
Yeah, so that's exactly the kind of thing I'm doing. Like this ring E is an example of that kind of thing. And we people definitely use this. I don't know how much it's used in published papers, because this whole subject is somehow relatively new in the sense that the Taylor-Wiles argument is from 95. This more functorial perspective is maybe from 10 years later. And then really connecting this functorial perspective to rep theory is maybe from only like 2010 or later, like in the last 10 years. But sort of working with these, at least thinking about these projective generators and the endomorphism rings and so on, and these orders in matrix rings, is certainly something that people, I'm thinking of like me, Andrea, Toby G, Bao Lehung, and Brandon Levin, sort of is something that people, my former student Daniel Lay, is sort of something that people do, but often informally, and they kind of tend to try and recompute things themselves. And one thing is, yeah, I don't think our field has an especially good sense of exactly like what's in all the modular representation theory literature, and also, you know, how our questions kind of compare to other questions, and to what people were interested in. So so one thing is that, you know, we certainly like studying these patching functors for GL2 of FQ is harder than GL2 FP. For example, the ring, so one way that would occur in the theory of patching functors is that this ring that I wrote down that's at the top of the blackboard now is a regular local ring. And so Cole-Macaulay modules are automatically free. Whereas the analogous rings that could come up if we were doing FP, if we were doing Q equals P to the F, the kind of rings you will get, there can be different examples, but the worst case will be that you have F X's and that you have F X's and F Y's, and each one satisfies Xi times Yi equals P for I equals 1 up to F. And when F is bigger than 1, that ring is not a regular local ring. And so Cole-Macaulay modules in that ring are not automatically free modules. But in fact, for example, Toby G and Dave Savard and I were able to prove that this patching functor does take these projective lattices to free modules by by studying various arguments with extension classes and co-socle and co-socle filtrations and things like this. So in this theory, one sees an increase in difficulty when you go from GO2FP to GO2FQ, but not in the kind of questions people have been asking so far, not insurmountable increases in difficulty. So yeah, so the idea of restricting to cyclic CLOP subgroup is, is not one that we kind of like, because we want to do GO2FQ. But somehow, again, for our questions, we've been able to get past it. So the wildness of GO2FQ doesn't seem to have bothered us. I don't know quite why. Like, I don't quite know why we've been able to kind of ignore the complications. But I think it's partly because we're very focused on these types and their reductions. And so we have a sort of, I don't know, I think that the thinking a lot about these types and their reductions channels the kind of questions we ask in a certain direction that avoids some of the pain that will be there if you were just sort of just purely studying the modular representation theory. So maybe is Jordi back? If he's the, should I start? So I wanted to just try and kind of phrase some actual explicit question, which is a question I first asked Jordi and then Raphael in an email thread that sort of got this thing going. I want to, sorry, I'll have to look here. I want to go back to these pictures for GO2FP squared for a minute. So there were, but then I'm going to draw them again because they're a bit of a mess here. But I want you to remember there were these 4 simples sitting in a socle filtration arranged in a square. And now I'm going to draw them again, but just to make it a bit easier to discuss, I'll kind of just make it more abstract. I'll just call them like sigma 0, sigma 1, sigma 2, and sigma 3. And again, what this diagram means is that we have the socle is sigma 0. And then the next layer in the socle filtration is the direct sum of these two. And then the top layer in the socle filtration, i.e. the co-socle, is sigma 3. And so that's a representation that exists. And we could just ask, I mean, that's a representation of gamma that exists, of GO2FP squared that exists, because I can make it by reducing this principal series or this cuspidal. So it definitely exists. But we could ask just a priori, why does this exist? So, for example, we know that this thing exists because we've computed the x's. And so that x1 exists. I mean, there's an extension. So there's a representation that has sigma 0 as a socle and sigma 1 as a co-socle, because we know that the x1 between those guys is non-trivial. And similarly, we know that there's a representation like this. There's an extension which has sigma 1 as a socle and sigma 3 as a co-socle, because that extension group is non-trivial. In fact, I guess they're one-dimensional, so these extensions are uniquely determined. But for example, there's no representation that does this. You can't find that. So how do you measure such a thing? Well, one way to measure it, which is that's a little argument with X, is that you take this class A, which is this extension class, and maybe this extension class B, and you form the innator product of A and B, which will be in X1, so it will be in X2 of sigma 3 by sigma 0. So this A is in X1 of sigma 1 by sigma 0, and this class B is in X1 of sigma 3 by sigma 1, and the innator product is in X2 of sigma 3 by sigma 0. And the vanishing of that innator product, just by a little manipulation, is seen to be equivalent to the existence of this thing, which following I have to remember who coined it. Anyway, a 3-layer cake is what Stephen Miller calls it, a 3-layer cake. So the existence of this 3-layer cake is sort of an obstruction to its existence, which is this class in X2. So this 3-layer cake can't exist. But let me write it do it this way. This 3-layer cake does exist, because that's kind of what I know I can get by reducing a type. So what does that mean? Well, I have to do the same computation. I have to compute this unitative product. But if you think about what it means, it will kind of mean that, like, the A cut B, if I called, so this was A, this was B, if I call this C and this D, that will mean that A cut B equals C cut D in X2. Well, these extension classes, these A and B are only defined up to scaling. So it really only makes sense to us for them to be equal up to scaling. So really they span the same line in X2. And so, so that's what must be true. But do people know how to prove that directly? Do people know how to compute unitative? So this is a question. Do people know how to compute the X algebra, or maybe the subgroup of X algebra generated by the X1s? So the X algebra between the simples. Do they know how to compute the X algebra between the simples, and especially the part generated by X1s? They kind of have to see these relations in the X2. So that's kind of one question I have. So I think this is sort of an interesting question. And I don't know that it will solve, I don't know exactly what it would solve by knowing the answer, but I think it's, like, I think there are a lot of computations that the number theorists working in this field are making themselves, or referring back to older papers, where they're using a lot of kind of apparent coincidences. Like, they know certain representing characteristic 0 and they reduce some mod P and they compute things, and it's not very systematic the way we know things. And I think it's a pretty natural question to just ask, can we understand this X algebra and what the relations are? And just a related question, which is also related to X2, is, suppose I just take sigma 0. Sigma 0 doesn't deform to doesn't lift to characteristic 0 as a representation of gamma, right? It's sort of an algebraic representation. You can write down the same Weyl module in characteristic 0 as a representation of GL2 of the ring of integers, but not as a representation of GL2 of the finite field. So sigma 0 doesn't lift to characteristic 0. So there must be an obstruction in the deformation theory of sigma 0. You know, there's a gamma representation, there's a sort of deformation theory of gamma representations, and there's some obstruction to lifting sigma 0. So there must be some class in X2 of sigma 0 by sigma 0 that gives you that obstruction. And do people kind of know how to think about that class? And then if we were to take one of these extensions, sigma 0 by sigma 1, now if we were over GL2 FP, sigma 0 wouldn't deform and sigma 1 wouldn't deform, but this extension over GL2 FP, such an extension we saw was the reduction of a lattice. So this extension does deform. So some obstruction gets killed now. But if I was over GL2 FP squared, and that was just one of these edges, that still doesn't lift to characteristic 0. To lift to characteristic 0, I have to make the entire 3-layer cake. That lifts to characteristic 0. Do people know how to compute this deformation theory? Do they know how to think about those classes in X2 and to see what the obstructions to lifting to characteristic 0 are? And do they see why some things lift and some things don't? So basically, I feel like in this in my experience working on this stuff, we somehow figure out things about X and reductions of lattices and injective envelopes and what things embed into injective envelopes, kind of in some like very ad hoc, messy way. Whereas all those questions, like mathematics has natural ways to approach those questions via homological algebra. And it would be nice to kind of have answers to them that just uses homological algebra. And again, thinking about, you know, if you could sort of understand something like the X algebra of the simples, that's another way to understand the category of gamma reps. Like there's sort of a derived equivalence between the category of gamma reps and the maybe, well, maybe you have to look at the kind of the DGA or something that underlies the X algebra of the simples. But that DGA there's some, you know, Bar-Beck Morita type equivalence between derived equivalence between the reps of gamma and the kind of DG modules over the DG algebra of extensions. And maybe that's a good way to think for these patching functors, because these patching functors are exact and these extensions play a big role. And that might be a good way to think, except that in practice, it seems kind of hopeless because we don't know anything about these X algebras really, apart from computations of X1s. And we kind of know some relations in X2 a posteriori. So that's kind of, so Jordi asked me to say, like, what are all the things Matt would want to know about SL2FQ? So that's sort of what I would like to know about SL2FQ, is what are the, how to think about the X algebra between the direct sum of the direct sum of the simples, and how to kind of conceptually understand all the various facts, relations, and so on we find about it. And that's kind of what I have to say, I guess. Sorry for taking so long to say it.
Thank you very much.
You're welcome. I mean, thank you for listening for so long.
Can I go back to the question that Katarina asked
yes.
at the beginning? So what kind of, so the set of simples, so the weights, you gave an example where there are the composition factors of a single irreducible. Will they always come from composition factors from a certain set of characteristic zero irreducible or not?
So in the GL2 case, there'll be either the reduction of a simple, so this hypercube of simples, so the reduction of a simple in characteristic zero, so this hypercube of simples, or maybe a face in that hypercube. Depending on which kind of Galois representation you choose, you can kind of cut down from the whole hypercube to some face in the hypercube. But if you go to GLN, like if you go to GL3, there's a recipe which is, well, they're partial recipes and they're more complicated, but they would involve, for example, again, doing some weights that come from the reduction of a simple, but then applying some reflection that kind of switches alcoves. So this is a kind of Florian Hersig's thesis, describes what these so-called weight sets would be, and in some combinatorial way. So it involves reducing, so basically it involves reducing a simple, I mean, so like reducing a type, reducing a simple in characteristic zero to get a bunch of simples in characteristic P. And in the GL2 case, now that's all you have to do because there's only one alcove. But in the in the GLN case, you then do a manipulation to kind of, so for example, for GL3, when you reduce one of these tame types, there'd be 6 simples in the lower alcove typically and 3 simples in the upper alcove. But then for the weight sets that appear in the support of this patching functor, you would do some reflection. So you would end up having 3 weights in a lower alcove and 6 weights in an upper alcove. So sorry, I know that's a little elaborate, but sorry, I'm just going to stop the share since my iPad doesn't.
For GL2, do you know the example you gave us the description of this algebra E?
Yes.
For GL2FP, do you have a similar description for FP to the F, GL2FP to the F?
Yeah.
You have a similar description.
Yeah, it'll be a bigger matrix order with more X's and XI, those XI's and YI's in some configuration that's, and then even if you start adding more types, so if you start, you could think that you could kind of build up the whole representation category for GL2FQ by starting with one type and then adding a second type. So allowing more lattices and allowing those lattices to interact, and then throwing in a third type. And eventually, if you throw in all the types, you've got in the whole representation category. And so, so even in that case, people know what the rings are. That's my student Daniel Lay, and with others also more figured that out. And again, the patching functors are kind of known in that case, and they basically proved to be unique. And in fact, Andrea and Daniel together showed that even essentially the Heck actions are also kind of basically uniquely determined.
Yep.
So these functors are in some sense in the GL2 case, more or less intrinsically characterized by their properties. So I didn't give you kind of all the properties. I gave you the key kind of abstract properties, but there's some, you have to know a little more specifically what the rings are for certain special cases to kind of start getting precise characterizations. But for GL2, they're more or less characterized in this way. For GL3, less so. But again, in number theory, we care about them not just on the reps of the finite of GL2 of K, but on GL2 of the ring of integers. And there they're not there we don't know how to prove that they're kind of uniquely characterized. Part of what I'm doing by trying to probe this GL2FQ case more, even though in some sense it's completely understood, is to find better methods and conceptual understandings, because it seems that like to handle the case of GL2 of the ring of integers, you won't be able to do it by the brute force computations that played a role in this GL2FQ case. And we feel like, you know, there's sort of seem to be deeper connections and phenomena happening that I mean, Toby and I and, you know, the people the younger people that we've kind of talked to and so on over the years, I mean, we've felt lots of suspicions about these situations and connections for, you know, maybe almost 10 years now. But But I think hopefully that gives you some sense at least of why I might care about these questions about X algebras. Because I think these relations in these X algebras just look, and even the possibility of this sign switch and the fact that as you move around these hypercubes, you get certain sign switches. It's like an interesting structure, and I don't really know how to like what it means kind of in some more conceptual way, or in some like kind of X algebra language, but it's that science, that kind of possibly like the R to the goes, you know, the +1 or -1 thing, and the fact that they have to be in certain orders for things to match up. It's just, this is interesting structures, and right now they look very combinatorial. And yeah, I would love it if they looked more conceptual.
Can I make one comment?
Mm-hmm.
So you mentioned the question about like, so like when sigma 0 has a leap, right?
Yeah.
So for G and Q, then actually we can answer the question. So when so put it this way, when a complex representation remains induced in modulo P, so this is like, but this is answered like for G and Q and for G and yeah. So it was a paper by Zaleski and myself where we proved that, okay, so if you add at least 3, then the only example that you can have is a linear representation inside of representation, one answer with some linear character. And yeah, so but of course you know that then for you can have the symplectic group over FP, and yeah, and also there's some related example with a symplectic group over FP square.
Uh-huh. So yeah, I think yeah, like I guess like in the case of GL2 of FP, I guess for example SymP -2 I guess lifts to a cuspidal. So that's like but I guess like in this GL2 case, like just for dimension reasons, it's pretty clear that most of these, you know, that these simples don't lift to characteristic 0. But it's kind of, but I guess part of my question is sort of, I mean, like the reason why is in some sense clear, like there's this dimension reason, but on the other hand, there is sort of there's an abstraction class measuring that, and like in some sense, like what is that class? Like basically this the X2, that's all the different statements about the reduction of these lattices and the existence of these squares and hypercubes and so on. They're kind of they're carrying information about X2, and they're carrying information about some massive products maybe and things like this. But no one is studying them that way. Like they have all this a posteriori information about relations in X2. I think it would be kind of interesting to make that information kind of a priori somehow. Or even, to look at that and deduce something. So go on.
Yeah, I mean, like, in terms of the question about lifting, then I think that so the reason why the representation of P and Q in general don't lift, I mean the molar representation don't lead to complex representation. So the reason is like, so if you take any complex representation of P and Q, then you can realize this over a unramified extension of Q, and the like so like unramified above P. And then, so one abstraction is that you want to have like x1 between phi and phi to 0. That's one. And then, so that's the way that, I mean, the way that Zaleski and I answered the question was that to use the fact that you can realize your representation over a unramified above the extension of Q, and then and somehow it's related to the Jordan structure of unipotent element.
So where's the paper?
Oh, it's in a proceeding of the LMS in 2002, I think.
Great. So I'll look. So thank you very much.
And I have another question.
Yeah.
So you mentioned that the claim type. So do you have wine type?
Yeah.
So what are the wine types?
So I certainly can't. I mean, well, one example will be it's kind of analog to principal series where you had like a Borel in Z mod P squared. Like if you induce kind of from Borel in Z mod P squared to GO2 of Z mod P squared, you'll get kind of wild principal, and you took a kind of a C star valued character of the torus that was really of conductor P squared. There will be examples. But in general, I mean, again, Andrea maybe has a better chance to write down examples than I do in the classical case.
Actually, they are the kind of things that appeared in Jessica's talk, probably, if you landed there. They're the kind of things that appear from Muse construction when you try to build Caspillo representations. They are classified for GLN over any finite extension of QP, and then there are other constructions that work for all groups.
But roughly, so a rough story, but which is probably more true for GLN and probably like less true for other groups, or more like you have to have more caveats for other groups. But a rough story is that if you look at the Bernstein, if you look at reps of a p-adic group like GLN QP, they arrange in continuous families. There's like the principal series is a family. Each cuspidal is basically its own. Each supercuspidal is more or less its own family, and those families are parameterized by affine varieties, very simple affine varieties, which are called the Bernstein center. And if you look at one of those families over a given component to the Bernstein center, since at least heuristically the family is deforming kind of continuously, but if you restrict to GLN ZP, that's acting through finite quotients, and you're in characteristic 0. So it can't really deform. Its representation theory can't deform. So the restriction to GLN ZP stays constant on a component of the Bernstein center. So you're getting these kind of fixed, infinite dimensional GLN ZP reps, but the GLN QP action is kind of varying continuously. But of course, but it will turn out that basically in that infinite dimensional GLN ZP rep, so it's a direct sum of all these E reps, which will be kind of a larger and larger conductor, meaning that like as you go along this series of GLN ZP reps, the congruent subgroup that acts trivially is going to get deeper and deeper. But there'll be some kind of slowest conductor member of that infinite family of direct sum ends, which will be the type, and is sort of distinguished as being like the simplest, in some sense, GLN ZP rep that appears in that decomposition. And for example, it will appear with multiplicity 1. This is the GLN story. It'll appear with multiplicity 1. And so that's, so these types are certain specific GLN ZP reps that I think from the point of view of, rep theory of GLN ZP, I don't know that people I think if you just study the rep theory of GLN-ZP, I'm not sure you would ever discover this notion. It's sort of, you discover it when you study how GLN-ZP interacts with GLN-QP.
It's just like minimal K-types in real groups.
Yeah, exactly.
So it's like very difficult to say what a minimal K-type is without knowing what the real Lie group is.
Yep. Yeah. So, I mean, they exactly play this role. And like, for example, the multiplicity 1 statement is related to the fact that the Bernstein center is really commutative somehow. So, so that's, but it just turns out that kind of for these tame cases where you're really factoring through GLN FQ, every EREP does turn out to be a tame type. But again, the connection, the sort of one of the connections with GLN QP theory or GLN, K theory will be that if you, for example, if you take a cuspidal, representation of GLN FP, sorry, and you compactly induce to GLN QP, and you fix the character, and you fix the central character as well, then that is irreducible. That will be a supercuspidal. So this like Lustig idea of making supercuspidals of GLN, of a p-adic group by, I mean, probably, well, I don't know if it's, it's now like, as Andrea said, it's in lots of people's work, and it's like in, for example, Jessica's work. But it goes back at least to Lustig's article in Cavalis, I think. So, yeah, so these types are kind of things you can compactly induce to try and make EREPs, or more generally families of EREPs of the p-adic group out of the kind of compact group.
There's a picture that I'm not sure if it's correct at all, but if we look at this variety that you were talking about, this XY equals P, then there's kind of, this is like looking at a point at the local ring of some stack or scheme or something where these are all glued together.
Yeah. Are you telling me a picture or asking me about a picture?
Like, it's just so is this a correct picture? And like, do we get like a chain of P1s or something like this?
Yeah. Yes, there's sorry, I'm just being asked if I'm still in the talk, and I am. So yeah, well, there's this these two lines crossing will be they could be like part of a chain of P1s. It would depend a little bit on the setup, because there could also be, well, there are many caveats in that statement because of stacking structures and other things, but yes, that could be part of a chain of P1s. But again, the analogous pictures for FQ rather than FP, there's some sort of analogous pictures that they're more complicated. Like, for example, the you get interesting objects coming up, like an A1 whose origin has been replaced by a P1 worth of origins. So some like pretty horrible non-Hausdorff thing, not even locally Hausdorff, and but still sort of various. These seem to be, they play a role, and they play these things like that gluing in that chain of P1s is related to some X1s being non-trivial, like that those two irreducible components in that XY equals P thing. When you reduce mod P, like each of them are standing for one of the simples, and they were meeting in codimension 1 because their simples had an X1. So that's one sort of phenomena we see when we're looking at one of these patching functors, is that the kind of the patch modules for the simples will be supported on irreducible components in characteristic P, and irreducible, and there'll be relations of like XY equals 0 type. These kind of relations, and but if you have more than those, if you have like X1 Y1 equals P, or let's be mod P, so X1 Y1 equals 0 and X2 Y2 equals 0, there are 4 irreducible components which some of which meet in line. They're sort of surfaces, they're planes, and some of them meet in lines, but others just meet in at the origin. So the weights but they'll be labeled by 4 weights, and 4 of these simples, and the ones that meet in the line will be labeled by guys that have an extra 1. And the guys that meet in points will be labeled by things that are separated by a layer of a 3-layer cake. And so the kind of so the combinatorics of those components is also kind of basically a hypercube. So the combinatorics of the reduction of the type is sort of a hypercube. And the combinatorics, like if you write down x1, y1 equals 0 up to x, fy, f equals 0, and you think about those components and how they meet, and you draw some kind of intersection graph or something, you also get a hypercube. And those hypercubes sort of match. And I think it was noticing those hypercubes matching was kind of what started to trigger this way of, I don't know, this kind of this train of thought.
So here it looks like it's something like an isomorphism on higher X groups or something, this functor.
I don't know. I mean, I don't know. I mean, so there should be a fancier version of this functor where you see all weights at once, and you should be living over something that's more global in the sense that it's not a complete local ring, but actually like more like some kind of stack or something. Like maybe like one of these so-called EG stacks that Toby G and I constructed. And then one might conjecture that on the Hecker category, if you this functor is fully faithful.
Huh.
At least if you do a derived, well, if you think about it in a suitably derived way, maybe, then this functor might be fully faithful. This will be a kind of very optimistic conjecture. And so that sort of, yeah, all these modular representations and their lifts and the Hecker operators between them would all be kind of being converted into modules. And there's some, well, there's some cases you can compute where you see some rings like ZP adjoin XY with XY equals P popping out. That's kind of that can be thought of as a Hecker algebra on the rep theory side. But it also kind of appears. So some of these rings that I'm writing down are like a completion of a Hecker algebra. So if I put the Hecker action in on the rep theory side and applied them infinity, we might have seen where that X and Y came from in some situations.
Mm-hmm.
Yeah, sorry to be a little cryptic about it, but actually, like, that's a computation that Bao showed me very recently. So, and in general, like from our, like, the number theorist sort of point of view, studying these functors and is related to constructing a p-adic local Langlands correspondence, and these modules, or if you think more geometrically, these sheaves, this will be related to kind of an L equals P version of recent developments in the L not equal to P theory of Langlands, where people like Jinwen Zhu and Fag and Scholzer are trying to do arithmetic Langlands more geometrically. So yeah, so this is kind of an L equals P part of that story, but I think we're in a much more preliminary stage, but I think, but again, like I think the reduction, like even if you do like doing Langlands theory integrally in the over ZL rather than QL for p-adic groups is a thing that people do, and for GLN, Helm and Moss especially studied this a lot, and now they have more co-authors who are working on this sort of a thing. It's very interesting, but But ultimately, somehow the mod L reduction of the representations of these kind of p-adic groups or finite, like GLN of FQ, the mod L rep theory is not so different to the characteristic zero rep theory. I mean, there are differences and interesting phenomena, but they're sort of they're much less crazy than what happens in the L equals P case. So I don't know. I don't know why I'm just saying that to maybe like drum up interesting, or I don't know, to make what I'm doing sound more exciting or something. But I think it's I just think that like this L equals P thing like prompts these questions in modular representation theory. It provokes questions in modular representation theory. So yeah,
just
like
to do just to do some more pattern matching. So we also have these kind of fully faithful exact functors called like Zergel's functors and generalizations, and these are a very useful tool in establishing kind of Langlands type dualities.
So where do you? So I think of like Sergel. Maybe I think of like Beilinson, Sergel, causal pattern sort of things, and then I think of real groups or something. But how broadly does that kind of philosophy connect to things?
I guess it's, well, I don't know, probably, I mean, Raphael is the kind of one of the people that has really realized how general this stuff is, and Roman's another person. But I would say that somehow it's just like in simple situations, Zergel's functor is often that taking Hom from some very specific projective sees a lot more than expected.
Interesting.
And I was trying to work out if your picture can be phrased in that language, but so somehow instead of taking a projective generator, you take something much smaller, and then this miraculously sees, for example, like in the classical setting, it would be fully faithful on maps between all projectives. And this somehow lands in a world that's of a more kind of commutative algebra or combinatorial nature, which you can then perhaps compare to another world.
So yeah, so if you have any like just recommendation for kind of primers on these things, because I've found like Beilinson Sergel papers and so on pretty tough going. I would love to have like some just cheat sheet or just something that one could read that sort of is gives some indication of how to think about this is comprehensible to humans. And so unfortunately I have to head out just because it's like coming on to 6 and I have to switch out with my wife on sort of like kid monitoring sort of duties and so on. So sorry to run, but
thanks a lot. And these were great questions, and we can.
Well, thank you very much for listening and all the feedback, and everybody stay well. Bye-bye.
Yeah, just one comment, Jordi. I think that's a great perspective. It feels like there's at the end of the day, it feels most things end up being a bit like that, like what you say. So yeah, I agree. So there's one thing that's not too bad. It's in characteristic 2 for GLSL2, but where the projective cover of the trivial contains all irreducible characters. But you can't, I mean, the functor, because it's a symmetric algebra, you can't literally have a Sergel type Landau-Wurst theorem on the nose, so it can't quite work directly, but one feels like there ought to be something like that. Yeah.
So is my intuition totally wrong here that I would say it's more like every projective is injective, and so I have lots of Sergel modules, and so I don't really reduce my problem.
If you do things literally, exactly. Yes, that's a problem.
Yeah.
Exactly.
Okay.
One thing that I learned from Matt some time ago that I remember finding shocking at the time, but I shouldn't have, is that if I take any lattice so let's take any representation of a finite group over a ring of integers, then, generally, as we saw, when I reduce this mod P, it's not semi-simple, but I can, after a reasonably innocent extension of my lattice, I can arrange that I can find a new lattice such the reduction is semi-simple. I think The first time Matt told me this, I'm sure he said that it was due to fight, but then when I asked him again, he said, no, I never said that was due to fight. But I have no idea who this observation is due to.
Wait, can you repeat it, please, Jody? What's the statement?
Basically, if I'm allowed to do a reasonably innocent extension of my ring of integers, then I can always find a semi-simple lattice. So a lattice whose reduction mod...
Did Thompson prove that?
Sorry?
John Thompson? Chip, didn't Thompson prove that?
Thompson? Yeah, I think, but Thompson proved that it can find an indecomposable one.
Thompson is a lattice where the reduction has a simple header. It's a kind of opposite situation, Thompson.
Yeah, right. I mean, Thompson proved there all sorts of things can happen, if I recall correctly. I mean, TF should know better than me.
But it's Thompson more than fight, I think. Yeah.
Mm-hmm.
But I am puzzled by the statement that you said, because like so maybe I misunderstood what you mean by semi-simple. You said a semi-simple lattice.
The reduction is semi-simple. When you reduce mod p, you go from the integral thing to the thing over a finite field. The reduction.
No, but this is what exactly Zalewski and I proved, that if for instance, if you take real and Q, then you can never do that. I think that so the redundant proof is even more than that. I think that the proof that the reduction can never be semi-simple. So that's why maybe I misunderstood something.
We can look at the
statement of what you proved. I mean, you can definitely find lattices whose reduction is semi-simple. What is your theorem?
That was from GLNQ.
Yeah, this is for GLNQ. For instance, let's look at GLNP. Okay, then we prove that if you
GLNP, what does that mean?
GLN over FP.
Okay.
Over the time scene, and and n is at least 3. Then we prove that if you have a absolutely irreducible representation of GNP, and if you can find a reduction, a lattice where the lattice, I mean where the reduction has some simple summand of dimension larger than 1, then it should be the type of representation only.
I think there's no contradiction in mathematics, because are you fixing the field? You're fixing the field. No, you're not allowed to extend the field in which you find the lattice, like the coefficients.
Yes.
So Jordy was saying there's an extension where you can find this lattice. So over Q bar.
Yes. Yeah, I mean, yeah, you can take anything. I mean, it is large enough expansion. But of course, I mean, like in the segment that I said, we only look at the unramified above the extension. So maybe.
You usually need a very ramified extension to do that. So if you are looking at two-dimensional representations where the lattices are just a segment in the Bruchatis tree, you essentially just need to add more points to the tree, just so there is one point with semi-simple reduction, and that amounts to ramifying the coefficients. So what I said only works when the representation has multiplicity 1, but there are similar statements in general.
I guess you can do it by just doing an extension at P, no? Like you never need anything away from P, I think.
Yeah, yeah.